Thanks, Terry. Hello, I'm Bill Renopoulos, Business Development Manager for OEM and Partnerships at Ross Video, where I've been leading our company's efforts to provide open solutions technology based on AES67, Ravenna, and SMPTE 2110 to OEMs serving the broadcast and professional audio industry for the last 6 years. Let's start with a bit about remote production to set the stage. It is clearly a hot topic today as companies around the world have raced to maintain their existing workflows with their personnel dispersed in many off-site locations. Remote production is the new normal, and now that we've experienced its potential, is likely to continue to be a focus in the future. Historically, when we talked about remote production, we were referring to an OB or an outside broadcast van at a specific site like a sports stadium. The entire end-to-end production was done in the broadcasting truck. And what we meant by remote is that it was done outside of a traditional studio. Over time, this evolved into REMI, or remote integration, a model which relied on a production control room within a centralized studio to run multiple off-site events. Not only did this allow the scaling up of production workflows, but it substantially reduced the need to send crews to multiple locations, which was not only more efficient, but resulted in significant cost savings. The shock of the last 2 years resulted in another big evolution, or perhaps revolution, in remote production, where the previous centralized way of doing things no longer worked as production professionals were dispersed in many different locations and couldn't work side by side. Now there was a need to maintain existing production workflows while allowing employees, operators, and talents to work from anywhere. We all know the story. Companies scrambled to make this work and had to deal with multiple different unknowns, including bandwidth-constrained environments. While many solutions were hastily cobbled together and a lot of trade-offs were made, there is still a need for higher quality productions with lower latency that integrate easily with existing equipment. This is where AES67 and transporting it over the WAN comes in. Live audio networking is a key piece of the puzzle, with the requirement to route it over a wide area network, including both public and private clouds over distance. To test out whether it is possible, a group of AES67 companies got together on an intercontinental AES67 over WAN demo utilizing the public cloud. This was an outgrowth of several experiments that we performed at Ross in North America with our equipment, involving large but modest in comparison distances of 500 kilometers or so, which included not only transport but also some audio processing in the cloud. A lot of effort, planning, and coordination went into this global proof of concept. It involved equipment from 3 companies across 4 different sites over 2 continents and leveraged the public cloud infrastructure from Amazon Web Services. I know some of you are anxious to jump into the proof of concept results, but before we do that, I would like to review our goals and objectives for this effort and provide some background on the challenges. This will be followed by a quick description of the setup and the equipment at each site. We will then take a look at the demo results, which will be followed by a summary of what we learned. Finally, we will wrap up with an outline of topics for future study and Q&A. Let's start with the why. Why did we bother with these AES67 over WAN experiments? We wanted to understand if we could send AES67 traffic over the public infrastructure and the cloud. The basic question is, can we do it? And can we do it across long distances? Even if we can, are we able to listen to something resembling audio? Would it be good quality? It is one thing for a single company to do it with their own equipment, like we did at Ross in North America, but could we interoperate with equipment from other companies, which is the whole point behind AES67? Finally, how could we do it? What challenges would we face? First, some background. AES67 uses IP, but it was designed with local area networks in mind that are synchronized to precision time protocol, or PTP. Packet loss is not an issue in the LAN and wasn't considered as part of the AES67 standard. In other words, AES67 doesn't work if packets are dropped, which happens and can be quite frequent at times in the public network. Having said that, AES67 and Ravenna have been proven and are being used in WAN applications across private networks, even though WAN applications were not contemplated by the standards. Private dedicated networks, whether owned or leased, are architected well and come with performance and service level guarantees. This is not the case for public networks. Public networks are the equivalent of the Wild West. You never know what you're going to get. You can't control them. They are congested and unpredictable. They don't use PTP-aware switches, and there are no quality of service guarantees. Public networks suffer from packet loss due to link failures and have large, sometimes dramatic delays due to packet retransmissions. The public network is a very harsh environment for AES67. Let's examine the three main challenges. Increased latency and packet jitter is definitely a problem. Drop packets, how do we deal with them? And timing and synchronization, which is always a challenge, but more so in this situation. Now, let's go into a bit more detail on each of these. The increased latency and packet jitter would normally be a massive challenge. Ravenna receivers and some AES67 receivers handle this by design with large receiver buffers. These can compensate for the added delay. Ravenna requires receiver buffers to handle at least 20 milliseconds of latency or delay, while AES67 specifies a minimum of 3 milliseconds but recommends 20 milliseconds. Most well-designed AES67 solutions, like all the equipment used in this demo, come with even larger buffers and can handle much more latency. The AES67 Standard Working Group, which is focused on the use of AES67 in the WAN, has issued guidelines, and one of its key recommendations is to increase the minimum buffer size in AES67 solutions. In summary, the increased latency of the public network is not an issue for Ravenna or well-architected AES67 solutions that have adopted the standard's optional recommendations for larger receiver buffers. Next challenge, packet loss. This is an important one. Ravenna and AES67 are not designed to work with drop packets, as mentioned earlier. Fortunately, there are other transport protocols that are architected to deal with drop packets without introducing a lot of extra latency. These were mainly designed for video, but can work with audio. Examples of the most popular ones are SRT, ZIXI, and lately RIST. In this demo, we solve packet loss by encapsulating AES67 traffic within SRT. Some may cry foul here and claim that we are not actually transporting AES67 if we are using SRT. But you can think of SRT as just a wrapper, and no way does it alter AES67 packets. The audio is still transported end-to-end as AES67. The final but significant challenge is timing and synchronization, which is key to Ravenna and AES67. We start by having a separate PTP GM at each site which is synchronized to GPS. All the equipment at each location is locked to PTP locally. No PTP packets are sent across the WAN or through the cloud. This is not currently practical as packet jitter is too high. Since the PTM GM at each location is locked to GPS, we can maintain synchronization across the WAN. This is how we attempt to solve this challenge. Now let's take a quick look at the equipment and setup. Now before going through the results of the demo and discussing what we learned, I want to zoom out again to the big picture and the block diagram architecture of the demo as summarized in this graphic created by my Ross Video colleague, Angelo Santos. On site in Ottawa, MITTWEIDA, Lausanne, Grenoble, various pieces of AES67 equipment from Ross, Direct Out, and Merging were used to create and receive AES67 streams. Gateways integrated or external at each local area network wrap these streams into SRT flows using HiVision's open source SRT implementation, which were then sent to the nearest AWS cloud access points using the public internet. The flows were then transported over the AWS cloud infrastructure between the access points, from where the secure SRT flows were then handed off to the local SRT gateways over the public internet again. The gateways unwrapped the AES67 streams at each local site so they could be received by the AES67 devices. All the AES67 equipment were locally locked to a PTP-GM at each site, which in turn were synchronized to GPS. This ensured that all the AES67 devices were synchronized to the same source, allowing the generated streams to receive the exact RTP timestamps, which were then transported transparently through the cloud. This provided deterministic and stable playout latency, allowing the receiving endpoints to be configured to compensate for the delay and to align the incoming streams. Since the streams were not modified or altered in the cloud or by the SRT gateways, the audio data was transparently sent from the source to the destination uncompressed and at full quality as expected. Let's explore the setup in North America at Ross Video. In our Ottawa labs, we generate AES67 sources from 2 different platforms, each in separate physical locations a few kilometers apart. In our main site, we used our SoftGear COTS-based microservices platform. Our SoftGear platform transmitted the AES67 stream to an external SRT gateway, where the stream was wrapped into an SRT flow and then sent via the internet to the cloud. At the same time, the SRT flows from Europe were received from the cloud, and the AES67 streams from the SRT gateway were sent to the SoftGear platform and were also transported to our nearby Canada lab via the Ross local area network, where they were received by IGI, our compact audio over IP bridge. The SRT gateway consists of a Linux server running Haivision's open source implementation. Setting up the SRT gateway is very easy to do and very quick, taking even first-time users 45 minutes or less. In this case, we decided at Ross to use an external gateway. In past demos, the functionality was integrated into our SoftGear platform. For synchronization, we connected all the Ross AES67 equipment to a PTP Grandmaster that is locked to GPS. Although we are only focused on transporting this presentation, we did run a successful experiment at Ross, which also included processing in the cloud. In that case, we sent AES67 streams to AWS, processed the audio using a Nielsen watermarking and coding application that we ran in the cloud, and sent the AES67 streams back to our lab. Here are some screenshots of the configuration setup of the Ross video equipment from the live demo. Both SoftGear and IGI use our standard dashboard controller tailored with custom panels to fit the needs of each product. As this demo used equipment from 3 different AES67 suppliers, we will be showing screenshots from them as well. Now turning our attention to Europe, we start with the setup at Merging Technologies, which involved 2 locations, Merging headquarters in Lausanne, Switzerland, and 200 kilometers away in Grenoble, France, where Nicolas Turmel was located and put together their part of this global demo. The Grenoble location used Merging's audio device, a virtual sound card, to generate and receive the AES67 streams. At the Lausanne site, an Anubis was used, Merging's compact A-to-D, D-to-A interface with fully featured monitor controller that integrates well with digital audio workstations. In this setup, SRT was hosted on a separate external gateway connected to AWS in Frankfurt. Merging used a SoundFX Grandmaster locked to GPS to synchronize all their equipment to PTP. The setup and user interfaces for Merging's audio device software Anubis are shown in these screenshots taken from the demo. In the Anubis display, the STP settings and the playout delay are displayed. The STP settings were configured manually and were the same for all the equipment in this proof of concept demo. Turn to MITTWEIDA, Germany, and Direct Out setup. It was put together by Claudio Becker-Foss, who presented recently. Direct Out used their Prodigy modular audio converter with a RAV2IO AES67 Ravenna card to generate and receive the AES67 streams. Direct Out incorporated the SRT gateway functionality into their Prodigy converter, which communicated directly over the public internet with AWS in Frankfurt. One novel piece of their setup is that Direct Out used an inexpensive PTP GM based on a Raspberry Pi that was tied to GPS. A very handy solution in the field that gets the job done when a full-blown Grandmaster is not available. Here are 2 screenshots from the Prodigy user interface, which highlights the network offset delay of the received stream from Ross in Canada and the one from Merging in Switzerland. As expected, the received stream from Ottawa, originating from much further away, has a higher network delay. We have shown multiple screenshots of different controllers and customized user interfaces from several companies supporting AES67 and Ravenna that participate in this proof of concept. As an aside, This shows the power of innovation driven by open standards like AES67. Different equipment ranging from a virtual sound card, cost-based platform, compact and modular audio converters to an audio A to D D-to-A solution for the recording industry built by different companies, all connected together as envisioned and enabled by AES67. To help visualize what was happening during the demo, Nicholas Turmel established a local loopback server hosted on AWS to monitor streams. He also created a monitoring app to analyze the AES67 packets and this web page to display the results. This allowed any participant during the demo presentation to listen in on the live streams via HTTP link within a web browser. Users could click on any individual stream to listen to the audio being received at that location. The web page included live volume unit meters along with network delay and accumulated packet loss statistics per stream at each site. We kept all the equipment up and running along with the website for another 15 days after the live proof of concept presentation and advertised it on the Ravenna site to allow anybody to easily access it and experience it at any time during that period. Now we'll review some results and what we've learned. First, we can send AES67 over the public WAN utilizing the cloud. That's awesome. We were very excited about that, and it literally worked right out of the gate. Local-only PTP synchronization locked to GPS works just fine. Packet loss was handled well by the SRT protocol. However, due to the occasional packet retransmission, the receivers had to be configured to handle more latency to manage the longer packet delay variation. Connections were set up manually. Latency, which ranged from 200 to 600 milliseconds, is lower than what we anticipated but still significant and heavily dependent on the quality and bandwidth of the local internet connection used to get to the cloud. It is important to use the closest cloud access point possible. There was a last-minute attempt to connect to ROS equipment in Brazil. The AES67 Brazil streams were accidentally sent to AWS in Virginia via the internet instead of using the local access point in Sao Paulo. Amazingly, the audio was still playable but not high quality, as was mostly transported over the best effort internet instead of the cloud. To manage the increased latency, we had to manually tune the link offset at each site as expected, but the deep buffers of the AES67 Ravenna receivers were easily able to handle the network delay. As mentioned, this is a proof of concept demo and we are very pleased with the results. It required some experience and fiddling with manual settings to get it to work. There are a few items that require further study to make it more practical and a usable solution. A big one is how to transport timing through the cloud. Quite a few companies are studying it. We consciously decided on manual connections using STP files to keep things simple. It would be very valuable to be able to use Ravenna or NMOS to automate the connection process. Ease of use would be greatly enhanced if the link offset could be handled automatically to compensate for network delay. To manage packet loss, it would be interesting to learn if SMPTE 2022-7 redundancy would work. Although SRT worked great, it would be good to experiment with RIS to understand if there are any performance or reliability benefits. In summary, the POC showed there's a lot of promise for AES67 in the cloud, and we are eager and motivated to tackle these open items in the near future. Thank you for listening. Now it's time to answer any questions. Thank you everybody for attending this presentation. Now I'll turn it back to Terry.